On a paper machine, an endless fabric races overhead at well over 1,000 meters a minute, carrying a fragile sheet of wet pulp. Just beneath it, fixed and silent, a row of ceramic elements drags the water out through their slots while the fabric slides across their faces. A plastic part here would wear away in weeks. The gray blade turning here barely changes for years, smoothing the way rather than grinding it down. What sets silicon nitride apart begins at the surface. It can be finished extraordinarily smooth, so the fabric glides over it with little friction. That means less wear on the costly forming fabric and less power drawn just to drive it. Where a rougher ceramic would scuff the weave and waste energy, this face lets the wire run light and last longer. The harshest moment comes at startup. The fabric runs dry for a moment and heats the element by friction. Then the water rushes in and chills it in an instant. That swing cracks many ceramics, but silicon nitride takes a temperature drop of around 600 degrees without flinching. Its thermal shock resistance is among the highest of any technical ceramic, so it shrugs off the very shock that would shatter a lesser material. Endurance is the rest of the story. Hard enough to resist the abrasive slide of fabric and fines hour after hour, silicon nitride wears away only slowly, holding its edge and its flatness. Yet unlike most hard ceramics, it is genuinely tough. It resists the chips and cracks that accidental impacts cause during cleaning or installation, so an edge stays true instead of breaking away. All of it traces to a bond between silicon and nitrogen. The two share electrons in strong covalent links, building a stable, hard, chemically resistant solid that holds up in hot, wet, and abrasive surroundings. For a dewatering element, a dense, gas pressure-centered grade is used, fired until the body is fully consolidated and ready to be ground to a fine surface. Its real secret, though, is the shape of its grains. As it sinters, silicon nitride grows long, needle-like crystals that interlock like felted fibers, forcing any crack to bend and bridge around them instead of running straight through. That woven structure is what makes it so tough, and because the grains are fine and even, the polished face comes out exceptionally smooth. While a low thermal expansion keeps it calm through every hot and cold cycle. Since a forming section is built to the width of the machine it feeds, each element is made to that deck rather than to a fixed size. Lengths are built up to span the full fabric width. The cross-section is shaped to the foil or suction box profile it sits in, and the wear face carries the slot or hole pattern the dewatering calls for. Leading and trailing edges are ground to a fine, exact geometry so the fabric meets them without a step. From there the design is tuned to the position. The blade angle and edge radius set how aggressively water is pulled, the slot width and spacing match the grade and speed, and the ceramic is bonded to a stiff composite body by a mechanical form fit so the surface stays dead level. Each face is finished to blend seamlessly into the deck, leaving no step to mark the sheet. Nowhere does this part prove itself like the forming section of a fast paper machine, where the wet web first takes shape. There, the fabric and sheet sweep across the element at full speed while water is drawn down through its slots, and any roughness or wear shows up instantly as a marked sheet or a shredded fabric. Silicon nitride answers on every count. Its smooth face keeps the fabric whole and the drive power low, its thermal shock resistance carries it through every start and stop, and its hard, tough body holds the exact profile that shapes clean, even paper. The faster the machine runs, the more its advantages show. Ultimately, the part the paper never sees is the one that decides how good the paper looks.